Hi everyone, let's continue our chapter, which is extrusion process. So what is extrusion ratio? How much reduction is possible? So the measure of reduction, we call it as reduction ratio, which is expressed as reduction ratio equal to A naught over AF, where A naught is the cross-sectional area of the starting billet and AF is the cross-sectional area of the extruded part or final cross-sectional area. So the amount of reduction is expressed in terms of a ratio called reduction ratio, which is A naught initial area by AF final extruded area. This equation can be applied for both direct and indirect extrusion processes. Now, which materials or which metals can be extruded? Which metals can be easily extruded in hot or cold conditions? Aluminium, copper, magnesium, zinc, tin, and alloys of these are easily extruded, easily extruded. Steel alloys are extruded in hot conditions. Soft steels can be extruded in cold conditions also. Other metals such as titanium and refractory metals may be extruded, but with certain difficulties. So aluminium in general, aluminium, copper, magnesium, these metals can be extruded very easily in comparison with hard metals like steel alloys and titanium. Now, what is the effect of extrusion die? The effect of extrusion die, as you can see here in this graph, this is the die and this is the die angle. So material is forced through the die and material will undergo plastic deformation and it will come out through the die opening. As you could see here, as the die opening, if the die opening is very small, if the die angle is very small, I'm talking about the angle, if the die angle is very small, then the frictional force acting between the material and the container walls will be very high, and even the friction at this area will be very high, so that more force or pressure is required for extrusion. So if it is a low die angle, then the frictional pressure will be high between the material and the dies, and as you could see here, at an optimum angle only less amount of ram force is required, and if we keep on increasing the die angle, if we increase the die angle alpha at a higher side, we can see the redundant work at the higher angles of alpha. So we need to go for an optimum angle. We need to select an optimum angle at which ram force required for extrusion will be less. At initial or at lower values of die angle, you can find that the ram force will be higher because of high frictional resistance. This is a typical die opening which is shown here. Now, this is already explained. Lower die angle, the surface area is large, which increases friction, and large die angle, more turbulence in metal flow, reduction in metal flow during the reduction. Turbulence increases ram force required. This is the effect of large die angle. So optimum angle we need to select based on the work material, billet temperature, and lubrication. Orifice shape of extrusion die. Simplest cross-sectional shape is circular die orifice. But a shape of die orifice definitely is going to affect the pressure or force required for extrusion process. As cross-sectional area or the shape become complicated or complex, higher pressure or higher forces are required for extrusion. So effect of cross-sectional area can be, or cross-sectional shape can be assessed by a factor, and that factor is named as shape factor, represented by Kx. You can see here a complicated fin, heat exchanger fin is heat exchanger sink is shown here. So the shape factor need to be accounted in such shapes to be included in the equation for calculating the real force or pressure required for extrusion process. What are the materials which can be extruded? What non-metals can be extruded? The non-metals are rubber, plastic, solvents, even candy, glass, etc. can be extruded. Products like these are the materials, non-metals I said, and then products, window seals, door seals, hose and tubings, wire insulations, candy canes. These are the products produced by extrusion process. Now this is a simple example of candy canes extrusion, and it is fed through the cone rollers, and finally you get the output. This is an example of, you can see here, the window seals, cold feed extrusion. Material is fed here, and this is the extruder, and it will come out through the die, and then we get the final, and it is taken through a belt, and finally we get the product. This is the die opening, the shape of the die opening. This is extrusion of plastic bags. As you could see, the die shape of the die is like this. It is extruded like this, and then cutting and sealing is done afterwards. So there is an extruder for this. So even non-metals can be extruded, as I explained before. So extrusion presses can be either horizontal or vertical. Horizontal are very common. Extrusion presses usually driven by hydraulically or by using mechanical drives, etc. Now, direct and indirect extrusion processes. As you could see here, if the direction of the ram and direction of the product in the same direction are same, we call it as direct. And if the direction of the ram and the product and the product are in opposite direction, as you can see here, direction of ram and the product are in opposite direction, we call it as indirect extrusion. This is a direct extrusion by which we can produce solid parts like rods, etc. This is a direct extrusion process by which we can produce a hollow, a tube like circular, rectangular, or channel shaped tubes we can produce. So in here, a mandrel is attached with the ram, and this will produce hollow sections. Similarly, here you can see this is for producing solid rods, and this is for producing hollow tubes. So similar things, this is basically the difference between direct and indirect, and main difference is, as you can see here, as the friction opposes the flow, direct extrusion needs more force in comparison with indirect. In indirect extrusion, the direction of force and friction in the same direction. That's why friction will help in the movement of the final finished product. So let us see the process dynamics, the variables of extrusion process. Reduction ratio, as I explained before, D naught is the initial diameter of the billet, and the corresponding area is A naught, and it is extruded to a final diameter DF. So final area becomes AF. So how much reduction is possible? Reduction ratio is Rx, which is initial area by final area. Using this, we can calculate the reduction ratio. Now we have the strain. So already we have studied about the reduction ratio. How much strain? Definitely strain, plastic deformation takes place. Strain will come into account. The strain without any friction, that means we can say ideal case. Ideal strain without any friction, log Rx, reduction ratio, log A naught by AF. So pressure applied in an ideal case, we can say the flow stress times strain, log Rx strain. Stress, you can say flow stress YF times log Rx, which is strain. Ideal strain will give you the pressure applied by the ram to compress the billet. Now we know that the flow stress we studied before, flow stress in plastic, in the flow curve in the plastic region, the average flow stress required is K strength coefficient times epsilon strain raised to n strain hardening coefficient divided by 1 plus n. This is called the average flow stress that need to be substituted here to find the pressure applied. Now we have the empirical equation proposed by Johansen for for estimating the extrusion, real extrusion strain is A plus B log X. A and B are constant Johansson's constants, where they are A 0.8 and B 1.2 to 1.5. And log Rx is already we studied is the epsilon, which is the ideal strain. We can say log A naught over AF, the ideal strain epsilon, which need to be substituted here to find the real extrusion strain, which is A plus B log Rx. Now we have the pressure applied for indirect extrusion and direct extrusion. Pressure required by the ram to compress in the case of direct extrusion using Johansson's extrusion strain formula is the average stress YF multiplied by epsilon X. Epsilon X is, remember, it is the extrusion strain. So extrusion strain in a real case, extrusion strain, which is a real extrusion produced by average flow stress, will give you the real pressure required for compressing or forcing the material through the die opening. In the case of this is indirect extrusion. In the case of direct extrusion, the pressure required is flow stress times this is extrusion strain using Johansson's formula plus 2L divided by D naught, where the term 2L by D naught accounts for the additional pressure due to friction at the container billet interface. So there is a friction, additional friction in the direct extrusion, as I explained before, that will be accounted by 2L over D naught. The ratio 2L over D naught will be accounted for the additional friction due to direct extrusion process. L is the portion of the billet remaining in the extruded, and D naught is the original diameter of the billet. So P is reduced as the remaining billet length decreases during the process. So with good lubrication, ram pressure would be lower than values calculated by this equation. This is the analysis of the pressure required for indirect extrusion, or the pressure required to force the material through the opening in indirect extrusion and in the direct extrusion. Direct extrusion, the pressure will be more by a term 2L over D naught, which accounts the frictional resistance. Now we can see that when we compare direct extrusion and indirect extrusion, we can see that the ram pressure required for the direction extrusion and the initial stage is much higher than the indirect extrusion because of higher pressure between the material and the container of the wall or with the die. And then as you could see here, as the extrusion begins and proceeds, the force required decreases in the case of direct extrusion, but indirect extrusion it remains almost the same. And at the end of the extrusion process, for both cases, the ram pressure required increases steeply because of the formation of butt. Now we can see here the force required is for direct and indirect extrusion processes. Here, for whether it is a direct or indirect extrusion process, force required is equal to pressure times area. Pressure, we can calculate it from the previous equations given here, pressure, and then pressure times the initial area of the billet will give us how much force is required for the extrusion process. Also, the power required can be calculated as force times the velocity, ram velocity. Using this equation, the power required for extrusion process can be calculated. As engineers, our aim is to find how much force or how much pressure or how much power required for an extrusion process. So power can be calculated as force in Newton times ram velocity in meter per second. Now the equations whatever we studied till now, they are based on a circular cross section, circular die orifice. If the shape of the die orifice changes, then the equation cannot be exactly what we studied before. So the shape of the die opening directly affect the force or pressure or power required for the extrusion. A complicated cross section means you need more pressure and more force compared to a circular orifice. So the shape of the die need to be taken into account whenever we design or whenever we calculate the force required or the power required. So how we can calculate it exactly is by a term called shape factor. What is shape factor? Shape factor is kx, which is 0.98 plus 0.02. This is an empirical equation times cx over cc raised to 2.25. Cx is the perimeter of the extruded cross section in millimeter. This is the perimeter or circumference of the extruded cross section in millimeter, and the cc is the perimeter of a circle of the same area as the extruded shape in millimeter. So cx by cc, this ratio raised to 2.25, if you multiply it by these two constants, you will get the shape factor, and cx over cc normally it varies from 1 to 6. So this shape factor kx need to be accounted or need to be used for calculating the calculating the force and the power. So as you can see here, the final equation P is equal to shape factor kx multiplied by yf epsilon x. If it is a circular die, then P is equal to flow stress yf time epsilon x extrusion strain only. But if the shape is changed to some other complicated shape, then you have to multiply with kx, which is the shape factor, which I already explained to you here. This is used to calculate or to account the change in shape of the complexity of the shape in the calculation. So kx multiplied by the stress, average flow stress times extrusion strain will give you the pressure in the case of indirect extrusion. In the case of direct extrusion, pressure required is shape factor kx times flow stress times epsilon x, the extrusion strain, plus 2L over d naught. So using this equation, we can find the pressure for direct and indirect extrusion processes. Thank you. Thank you very much for listening.